Hi, and welcome back. Now we've covered the introduction to random processes, and now we're going to look at several aspects. The first of which is stationarity in a little bit more detail. So, stationarity has to do with how the random process behaves as a function of the index. It could be time or space. One particular form of stationarity of interest is strict sense stationarity. Not all processes are strict sense stationary, clearly. Some processes are strict sense stationarity provided that they meet certain requirements. First of all, if it's strict sense stationary, then that means that the probability distribution function that is associated with the process, the joint PDF, does not vary with the change in the index. Let's take time as an example. If, for example, I'm looking at the distribution, the joint PDF or the joint CDF at times T1 to TK, and I now shift each of those instances by an offset tau, so each one, the relative separation between each of the time instance remains the same, then if the joint CDFs remain the same, that means they are invariant to a shift tau. So as an example, imagine I'm looking at T1 to T3, yes, where n equals, or k equals 3. If I take T equal 1, T1 equal 1, T2 equal 2, and T3 equal 3, those are times 1, 2, and 3 seconds. And I look at the joint CDF at that time. And then I arbitrarily shift that like think of it as a grid, and I shift it on the time axis so that T1, T2, and T3 remain fixed relative to each other, but the whole thing moves in the overall scheme. So let's say as opposed to 1, 2, and 3, I shift each of them by 5 so that the new T1 or T1 prime is now 6, T2 prime would be 7, and T3 prime would be 8. As you can see, there's a separation between them of 1 second between consecutive points. Yes? Now, if the joint CDF for 6, 7, and 8, or 5, 6, and 7, or 1, 2, and 3, whatever the shift is, same for all shifts in time, then the process is defined as being stationary. If, for example, now I look at 4 points and I shift them, but the same doesn't hold, then that means that it is nth order stationary, in which case it was stationary up to n equal 3, but it was not stationary for n equal 4. So this is another aspect of the stationarity that you need to be aware of. You may not be stationary across all n points. You may be stationary only across a smaller set of k points, right? And that determines the order of the stationarity. Of course, if you're nth order stationary, then you have to be stationary for all lower orders as well. So if you're fourth order stationary, then you should be stationary for third order and second order, right? Now, because of this, properties of strict sense stationary processes, one is that, and this is a way that you can test for stationarity, or it's a consequence of the stationarity, the mean function is constant. And that comes from the definition of the time or the index invariance. So if you calculate your mean function and you get a constant value over all index values, then that's one thing that must be maintained for strict sense stationarity. Another thing that must happen is that if you look at the correlation between any two time instants, it depends only on the time difference, not on the actual time samples. And if you have, there's another extension that deals with two processes. If the joint distribution of processes X and Y are invariant to shifts in time, then that's also called jointly strict sense stationarity. Another of interest is wide sense stationarity, which is one we focus a lot on in this course. It's not as restrictive as strict sense stationarity in the sense that we aren't expecting the probability distribution functions to be invariant to shifts in time. The only thing that we look at are the mean and the autocorrelation. So just because, notice the properties are the same as for strict sense stationarity in terms of the mean function and the autocorrelation. However, notice the difference. There's a difference, which is that the probability distribution function does not need to be invariant to shifts. There are also other forms of stationarity, such as seen here. You are advised to have a look at some of them. Now, food for thought. When a complete description of the random process is unavailable and you only have samples, and this is important for our modeling, how would you know what type of stationarity do you have? Think about it and we'll discuss it in the next class.